Game theory is deeply tied with the properties of convex sets. Okay, tied with properties of convex sets. I cannot get too deep into it with the limited time, but I still can state what are the main two important theorems. At least you know, knowledge can come in four forms according to the Indian tradition: Pratyaksham, Anumanam, Upamanam and Shabdam. Pratyaksham is what you see. Anumanam is by inference. Upamanam is by analogy. Shabdam means scripture. So, if the professor says, here is the theorem, you have to believe it. Okay? Don't question its validity. Of course, the teacher cannot pretend that I took it again from my teacher. That is useless. The teacher also must chew to find the formal proof. Okay. Anyway, the two important theorems which I state for granted right now is separation theorem. Separation theorem for convex sets. How many of you are familiar with the word convex set? Please raise your hand. Okay. Quite a few are familiar. If you are not familiar, the others can help because a lot of people. Okay. So basically a convex set is in n dimension is any set where if you take any 2 points and join them by a line, the entire line is inside the set. Okay. So for example, this is a convex set because if I choose 2 points and join it, this is my set. So these 2 points I join, the whole thing is here. This and this, the whole thing is there. So this is a convex set. This is not even if I had this piece of fruit, this is not a convex set because if I take this point and this point, if I join it, it is not inside the set. So you now know what is a convex set. Okay, you don't need more than that, but you need to write it down algebraically. So while geometrically you can see, algebraically you need to write it down. And suppose you think of this. You choose some 2 points in 3 dimensions. This is a piece of stone. Okay? Imagine it's a piece of stone and you have 2 points x, y. So x will have coordinates x1, x2, x3. Y will have coordinates y1, y2, y3. And then if I join it, any general point, any typical point, generic point can be written as some alpha times x plus 1 minus alpha times y, where 0 less than or equal to alpha less than or equal to 1. Okay? So it will have coordinates alpha x1 plus 1 minus alpha y1, alpha x2 plus 1 minus alpha y2, alpha x3 plus 1 minus alpha y3. Okay? Any point joining on this segment is of this type. Agreed? Okay. The next one more definition. A convex set is called closed. A closed set if you have a sequence of points, a convex set X in Rn is called closed if Xn belongs to X, n equals 1, 2, etc. and Xn tends to say X star coordinate wise implies X star also belongs to X. So the limit of a sequence of points, any points from inside the set, when it approaches some point, and that approached point must also be part of the original set, then you say the set is closed. It's a closed convex set. Okay. Then, what is the first important theorem? And again, let X, Y be two disjoint convex sets. Be two disjoint convex sets. X and Y are disjoint. There is no point common to X and Y in Rn, real n space. If X is closed and Y is closed and bounded, I want to explain the word bounded. What do you mean by bounded? It's our intuition. Okay, the intuition says the set is here. I can choose from the origin a huge ball of large size, and this set is contained inside the ball. Okay, as long as the entire set is contained inside a ball with center origin, we say that the set is bounded. That's all. You got it? Okay. So Y is closed and bounded. Then there exists a hyperplane that strictly separates the two convex sets. What do you mean by a hyperplane? So we need to imagine this first in 2 dimension. So let us look at what is a hyperplane in 2 dimension. Maybe I should close this and I will write in here. Come to you. Another expert. Oh, okay. Okay, leave it there. Because I have fewer slides to make in a short time, I am better off writing this, so it is also slow. So you are able to gather it. Okay. See, look at this. Here is a convex set in the plane. So this is bounded, you agree. So here is a convex set. Even though I cannot draw there, this is an unbounded convex set. Agreed? And it is closed. That means I am also including this boundary. All I am saying is I can draw a strict line in between these two sets. I can draw a line which strictly separates the two sets. This is called the separation theorem in R2. Now you take the same thing in 3 dimension. Instead of this, you think of some stone, and you think of, this need not necessarily be, as long as it is closed, it is fine. This is an orange. So you have to imagine it is a three-dimensional object. Agree? Orange. And if these two sets are disjoint, what does separation theorem say? You have a plane which separates the two. A plane which separates the two. That means I can put a sheet of paper which is in between the two sets, and the sheet of paper contains neither the points of this nor the points of that. So this is the so-called separation theorem. Now, how do you represent the equation of a plane? Okay? Huh? No, can you tell me louder?
Ax plus by plus cz plus.
Okay, so the equation of the plane Ax plus by plus cz equals d. Okay? This is a typical equation of the plane. Okay? Now, suppose this is that plane. Suppose I chose, that means any point x, y, z in this plane will satisfy this. Here it won't satisfy. Suppose I chose a point PQR, not PQR, say 3, 9, 4. This is a point in this one, suppose. So what is the thing which this theorem says in my language? I can say this is not on this plane, which is equivalent to saying if I put x equals 3, a times 3 plus b times 9 plus c times 4, it will not be equal to d. That's all it says. Agree? Suppose you compute and found that it is less than d, suppose. If it's not d, suppose it is less than d, then if I choose some point here, so 53, 14 and 7, okay, then I take a times 53 plus b times 14 plus c times 7, what can you say? It will be greater than d. For everything inside, it will be less than d. For everything here, it will be greater than d. It will be equal to d on this one. That is the strict separation theorem, nothing more. Okay? Now, I go to the these conditions are needed to prove the theorem, and we are not proving the theorem. You only understand the geometry of it. Okay. The next theorem is, if X is a convex set closed bounded and Y is a convex set with an interior point where x, y's are in Rn, they are in n space, and if x and y are disjoint, this is the notation for x and y disjoint, then there exists a weak separating hyperplane. So what is the geometry of that? Here is something, okay, it's a three-dimensional object, and then no, not like this. Okay, this is the x which is closed and bounded. Okay, now this is the other set y, okay, which is just a convex set, and it has an interior point. By interior point you mean there should be at least one point around which you can draw a sphere, and the sphere is completely inside the set. If you can do that, then the set has interior. So, for example, in this case, this you have to imagine it as a three-dimensional object, not as, okay. So there is a sphere which is somewhere here, which is contained. Then, if these two sets, in fact, you can even assume it need not be closed. That means points other than this so-called boundary, it can be there. Then what the theorem says is, we will be able to draw a sheet of paper such that one side this lies, on the other side this lies, but not with strict inequality, but with weak inequality. Okay, with weak inequality. So what do you mean by that? Now I want to translate this into algebraic statements. Algebraic version. So what it says is, in three dimension, we wrote the hyperplane as ax plus by plus cz equals d. Okay, so it is simply the inner product between abc and xyz. xyz is any generic point in three dimension. ABC is a very fixed point, some fixed vector, and then if you take the dot product, ax plus by plus cz is the dot product, agreed? And is the dot product. Or the inner product, whatever it is. And then this big theorem says ax plus by plus cz is less than or equal to d if if xyz belongs to x. It is greater than or equal to d if xyz belongs to y. So if there is something common, you cannot have because they are disjoint. So that is the thing. On the boundary it will be equal. That's what will happen. So this is the theorem which is used in proving the Minimax theorem. This is the theorem. I am going to now first show that picture. Here is a game. It's a two-person game. Player 1 chooses one of the rows. Agree? In this matrix. player 2 chooses one of the columns. Player 1 chooses one of the rows, player 2 chooses one of the columns. They are doing it secretly. Now if player 1 chooses the first row and player 2 chooses the second column, 2 must give 12 rupees to player 1. If he chooses player 1 chooses the last row and player 2 chooses the last column, player 2 pays nothing to player 1. Player 2 pays nothing to player 1. Now, what I do is, I try to represent, because we want to plot everything in the 2-dimension. We want to plot everything in the 2-dimension. All I am now doing is, all I am now doing is the following. Plot each row as a point in 2-dimension. Let's plot them. 312, is 312 here? 2, 3. This one is 312. Then 4, 8. 4, 8 is 2. This one. Then 6, 7. 6, 7 is row 3. R3 is row 3. And 8, 4 is row 4. 12, 0 is row 5. So each row is plotted as a point in the 2 space. Agreed? Now, find the smallest convex set containing them. That is the one which is shaded. Agreed? That is the one which is shaded. So now let us take, once you appreciate this is enough. Okay. Suppose you do the following. How many columns, how many rows are there? 5 rows. Say 1/5 times 312 plus 1/5 times 4, 8 plus 1/5 times 12, 0. Agreed? If you take that point will be inside this red area. Do you agree? You have to visualize that. Huh? Okay. So instead of 1/5 you could have taken anything. Suppose you could have taken 3/4 of this plus 1/4 of this plus the rest are 0. Okay? Namely, this is equivalent to joining these two points 312 and 48 and forming the line. Okay? Like that you can so any combination, that means any strategy of this player, with what probability he chooses this, with what probability he chooses this, and with what probability he chooses this, actually can be identified. With that you can associate a point in this set. Are you with me? Okay. But that point may have more than one way of representing it. That point may have more than one way of representing it. The simple reason is, suppose you have a set. So, suppose you took this point. This point can be represented by purely on the line joining this. It is also on the line joining this. So there may be more than one way of representing the same point. But its effect is same. Its effect is same in some sense. Okay. So there are two ways of playing the game. Secretly, you choose with various probabilities to choose the rows, or secretly you choose a point inside the set. They are same. in effect, secretly choosing a probability of choosing row 1, row 2, row 3, row 4, row 5 is the same as whatever is the outcome point that is kept secret. So they are playing the following new game. What is the game? The player 1 chooses secretly a point in this set. Are you with me? So player 1, let me write down, chooses secretly a point in the red set. It's chosen a point in the red set. Now, player 2 is the player who has to shell out the money. Agreed? So, he can choose the first column or second column. He can choose the first column or second column. If only somebody is spying what player 1 has chosen, assume, pretend as though somebody spied on what point has been chosen inside the set by player 1 and comes and tells player 2. What will be player 2's action? For example, suppose, let us take this case. I wish, okay, effectively I have to use this thing. Suppose this was the point chosen secretly, which is equivalent to choosing the first row. What will player 2 do? First column. So first column, what is the property of that one at this point? The first coordinate is smaller than the second coordinate. Now suppose he has chosen, say, some point, say like this point, the middle point of R4 and R5. Middle point of R4 and R5 is, what is that one? 10, 2. Agree? Is it not? That is the middle point of R4 and R. This is R4, this is R5. The middle point is, each coordinate simply take the half. That means it is 10 and 2. So 10, 2 is somewhere here. So what would, if some third person came and told him, then he would choose the second column. So he may choose the first column or second column if someone can divulge that information. Agree? But what will happen on this upper boundary? Look at this one. This is R1, R5. I can write down the equation of this line. Okay, that line is 4x plus 3y equals 48. Do you see? Because if you take this point and this point, the line joining these 2 points, that's the equation of the line is 4x plus 3y equals 48. Do you follow me? Okay. Now, any point, suppose you choose this point and go like this one and go like this one and choose any point here, it will have the property 4x plus 3y will be greater than 48. So, for any point here, it will be 4x plus 3y will be less than 48. Now, at this common point, what will happen? 4x plus 3y will be equal to 48. Okay. So, I can say the following. Are you with me? Please stop me if you don't follow this. This geometry is necessary to appreciate. Okay. So, but player 2 can simply choose if player 1, for example, if player 1 chooses this point, okay, which is equivalent to this point in this set is equivalent to choosing 4/7 the times 312 plus 3/7 times 12 0. Is it not? This point. You don't see that. Okay. Now, what is the property of this point? This is the y equals x line. So that means both coordinates are equal. If both coordinates are equal, and if the equation of this line is 4x plus 3y equals 48, what will be the value of x and what will be the value of y? Okay. Instead of put x equals y, then 7x is 48, so x must be 48 over 7. Okay, and whatever it is, y must also be 48 over 7. Okay, do you follow me? So player 1 can choose 4/7 0 0 0 3/7 to choose his point secretly. He can even tell the opponent, I have chosen that. He can even tell the opponent, I have chosen that. So now what will happen to the opponent? The opponent has to choose either the first coordinate or second coordinate. Either coordinate you choose, you still get the same 48 over 7. So that means the opponent must shell out 48 over 7 no matter what he does. You follow me?
So that point the coordinate is 48 over 7, that is how is this probability?
Okay. No, 48 over 6, because, let me, yeah. See, 4/7 times 3 plus 3/7 times 12 is how much? 48 over 7. Suppose he chooses this one, he is going to give 48 over 7. Now, suppose he chooses this column, he has chosen this with 4/7 times 12 plus 3/7 times 0, that will also be 48 over 7. So he has to shell out 48 over 7 no matter which column he chooses. Which column he chooses. So that means player 1 can get on the average 48 over 7 whether player 2 chooses the first column or second column. So I can say whether 2 chooses column 1 or column 2, 1 can expect 48 over 7. Are you with me? Is there somebody? Yeah.
Exactly the game.
Be loud.
What was the exact game?
The exact game? The game is this game. This is the original game. Original ordinary matrix game. Player 1 chooses one of these rows. Player 2 chooses one of these columns. And whatever entry is reached, player 2 pays to player 1 that money. Agreed? And what player 1 does is, instead of playing with mixed strategy, this is called a mixed strategy, all he does is he selects a point inside this set, okay, and he chooses the point 48 over 7, 48 over 7, okay, which is equivalent to this mixture. Which is, namely, if he uses this one, whether he chooses the first column or second column, the same number 48 over 7 will come. But can player 1 get more than that? Can player 1 get more than that? No. I want to show that, okay? So, all I am saying is, so I can say, while 1 can get an expectation 48 over 7. No matter what 2 does, 2 may choose the first column or second column, still his average income will be 48 over 7. But the question is, can player 1 get more than that? No, he cannot. I want to show that. So now look at I'm sorry. Okay. I have to show one. I want to say that player 2 can keep it, okay? Okay. Just a minute, okay? I need to do a small calculation. Okay. Okay. Now, okay, I got it. Basic idea is, now the equation of this line is 4x plus 3y equals 48. Agree? I can rewrite the same equation also as 4 over 7x plus 3 over 7y equals 48 over 7. Okay? Now, what is the property of these two sets? 4 over 7x plus 3 over 7y is less than or equal to 48 over 7 if xy is in the red set. Do you agree? Are you with me? 4 over 7x plus 3 over 7y is equal to 48 on this line. It is greater than on this portion. It is less than or equal to on this portion. So, now what I am saying is, suppose player 1 chooses this point, 312. He can choose the first row. See, player 2, what player 2 does is, he is going to choose the first column with probability 4 over 7 and the second column with probability 3 over 7, which is based on the representation of the separating line. It is a function of the separating line. Okay, so he has chosen the first column with probability 4 over 7, second column with probability 3 over 7. Suppose he chooses the first row. How much player 1 can expect? So 4 over 7 times 3 plus 3 over 7 times 12, which is 48 over 7. He cannot expect more than that. Now suppose he chooses this one, second one. It will be 4 times 4 over 7 plus 8 times 3 over 7. How much will it be? You follow me? 40 over 7. It's not more than 48 over 7. Suppose he chooses the third row. 6 times 4 over 7, which is 24, plus 21, 45 over 7, which is no more than 48 over 7. Chooses this, the same. Chooses this, the same. So player 2 doesn't have to care what player 1 does. He may choose first row, second row, third row. He can mix them with various probabilities. He doesn't care. Independent of whatever he does, player 2 on the average is not going to lose more than 48 over 7. If he is stupid to choose these things, he will even lose less. He will gain very less. Okay? So you are better off choosing these two with that. Okay. So we call this 48 over 7 as the value of the game, and this is a good strategy for player 1, and the other one 4 over 7, 3 over 7 on the top if you write as the good strategy for player 2. That's all. The theorem is only that. So if you assume the separation theorem, the Minimax theorem, now I am going to write down the general theorem. Can you push it to the previous slide? Yes. What does it say? There exist probability vectors x for player 1 choosing the rows, guaranteeing an amount v. There exists a probability vector y for player 2 guaranteeing loss no more than v. That is the Minimax theorem, and the basic proof which I gave is for a special case of 5 by 2 matrix. I can give it for 7 by 9 matrix or anything. This is the same. This is only a change of notation. Okay? Now, this was the theorem which was not discoverable by Borel. This was discovered by von Neumann when he was just a 20-year-old boy. Okay? And this is the breakthrough theorem, but he didn't give this proof. This proof was an ingenious proof given by a French mathematician, Villet. Before that, von Neumann's proof is something 20-25 pages long, going through small letters. If you look at this book, Contributions, no, not there. You should see Mathematical Annalen 1928. The German journal, if you look at 1928, the long proof, for pages and pages it goes. He himself has struggled like anything to get this theorem. Okay? But whatever it is, it was finally seen as a simple application of separation of convex sets. And then once it was seen as separation of convex sets, the convex sets became much more fundamental to the field. And slowly, the next genius was John Nash. Okay? John Nash came with an ingenious proof of the same theorem, okay, which I just want to explain. Okay? And by that, he went several steps ahead of von Neumann. John Nash went several steps ahead of von Neumann by proving a very general theorem, but his original idea was to prove only the Minimax theorem. This theorem has 8 or 9 different proofs by different mathematicians. Okay. Okay, so first I state the next fundamental theorem of convex sets. Theorem let S be any closed, bounded, convex set in Rn. Okay? Let F be a map of S into itself. F sends points of S to points of S such that F is continuous. What do you mean by continuous? We need to define what is continuity. Okay? You imagine intuitively, okay, that is, if Xn is a sequence of points belonging to S, and Xn tends to some X star. Xn tends to some X star. What do you mean by tending? Coordinate wise it is approaching. Okay? Then f of xn is also in S. Okay? So call it as say yn. Then if f of xn, which is equal to yn, goes to some y star, suppose it does, then y star should be equal to f of x star. Okay? So that is the thing which you should appreciate. So what it really says is, imagine this is your set S and some point x1, x2. So this is xn. So the image of x is fx. So this is f of x1, f of x2. Okay? Now this one ultimately it reaches a x star. Okay? Now this one ultimately reaches y star. Then when you take f of this, it should be this. Then you say the function is continuous. You have to, because I cannot rigorously define it to you now, because then I go through, I am running a course in calculus. I can't do that. Okay? So again, use the valid knowledge of the teacher, Shabda Pramanam, you believe it. So what the theorem says, f is continuous. Then there exists a point x hat in S such that f of x hat is x hat. The point goes to itself. There is at least one point which, when you take the f of that, is the same point. Okay? That's called Brouwer's fixed point. It's called Brouwer's fixed point. It's called Brouwer's fixed point. Okay. Okay. One more thing which I mentioned with this continuity. Okay. So maybe I can, because I have to tie it with the Hex theorem. Okay. definition, xn tends to x star in Rn if you know the norm of a vector. Do you know the norm of the vector? How many people know the norm of the vector? Please raise your hand. A reasonable number know. If you don't know, please come back to me, I will explain. Okay. If norm of xn minus x star as a number goes to 0 as n tends to infinity. There are several norms: Euclidean norm, L1 norm, L infinity norm. There are 3 different norms, important norms. Okay, so one of them is Euclidean. Norm of xn, norm of x is summation xi square is the square root, where x is this vector in Rn. Don't confuse this n with the, oh, okay, let me write down this capital N here. Okay. 1. Then this is, we write it as norm x2, this is norm x1. L1 is summation absolute value of xi. Okay. Then the third one is norm x infinity, L infinity norm. This one is maximum of absolute value of xi over all I. Now the one important property is, when xn goes to x star in Rn, it will go in this norm, this norm, this norm, in every one of those norms. They are all same. All these norms will have the same effect. They are all equivalent in some sense, in the, what I call, in the topology of Rn. Okay? 1. So now I want to, a major achievement in the last few years is to get hold of this fixed point in a constructive way. To get hold of this fixed point in a constructive way. Not that you are going to have it. You are quite happy if there is a point x star whose image f of x star, they are close to each other. Even though they, see, when it is a fixed point, it must be exactly 0. Namely, okay, let me write down. X is, x star is a fixed point if f of x star equals x star, or equivalently the norm of f of x star minus x star equals 0. Then you say that it is a fixed point. X star is an epsilon fixed point. X star is called an epsilon fixed point if norm of fx star minus x star is less than epsilon, where epsilon is chosen by you. You choose an epsilon positive and look for some point whose image from that point is not too far away, it is still to within epsilon. then you say x star is a almost fixed point or epsilon fixed point. So you know mathematically that you will not be able to find the fixed point in general, but you can get hold of an epsilon fixed point. You can get hold of an epsilon fixed point in a constructive fashion. In a constructive fashion. That's the idea. Constructive means, now I am going to show what is that constructive procedure. Let me take the example. I take an example and then generate it. Okay. Can you push the next one? Go to the next one. Okay. Now let us take the simple example. Okay. I'm going to take a simple example. You can get a copy of this thing, all of you, but right now you try to follow. Actually, directly listening and stopping me at every step is very important. Okay. I have to see, I take the square. This is the unit square. I choose any point, its coordinates are between 0 and 1. Then I have compute another point here. What is its first coordinate? It is x plus y plus 1 over 3. What is its second coordinate? xy plus 1 over x plus 2. Do you follow me? So I can plot that point somewhere here. It will be, because x plus y plus 1 over 3 is also going to be between 0 and 1. xy plus 1 over x plus 2 is also going to be between 0 and 1. Because xy is anyway less than or equal to x, 1 is less than 2, so xy plus 1 over x plus 2 will be between 0 and 1. So my function f of xy is this. And suppose I choose epsilon as 0.05. Epsilon 0.05. You follow me? Now what is the thing which I am looking for? I am looking for a point, and do you agree that these functions are continuous? f1 xy is x plus y plus 1 over 3. It's a very well behaved function. The other function is also well behaved in the whole interval 0 to 1, because the denominators are positive. So then top is continuous, bottom is continuous. Your baby calculus says that the ratio is also continuous, so everything is fine. So you can swallow those parts. Now there should be a fixed point. There should be a fixed point. I want to find what is that fixed point. Okay, that is equivalent to solving these equations. What is that equivalent to? It is equivalent to x plus y plus 1 over 3 is x, xy plus 1 over x plus 2 equals y. This is easy to solve now. Normally such a function you can easily to solve, but I can write a very complicated function. Then you will not be able to solve it directly. You may not be able to find x and y satisfying this all that easily. Okay, but I am only giving an approximate algorithm, to locate an approximate fixed point, namely epsilon fixed point. Okay. So what I do is, I make this into a grid. Okay. So in my case, I have chosen a grid of 10 by 10. Hopefully that is good enough. Otherwise you have to make 100 by 100. It's the grid. If you want more accuracy, you divide this into further thing. So the idea is it has something tied to a continuous function in the square is uniformly continuous. I don't want to get into that nonsense, okay? You can take your calculus and read it, okay? Now, I am basically relying on the property that continuous functions on the square are uniformly continuous. So, I am relying on that additional information so that I can make a grid sufficiently thin. Okay. Now, what I do is, I pad it with you need to imagine this is all squares. Okay. Okay. This point is 0, 0. This point is 0, 0. Okay. Now, this one will be minus 0.1, minus 0.1. Agreed? This one will be minus 0.1, no, 0 minus 0.1, blah, 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 okay? Now, I am going to, do you have another color chalk piece, different color? No. Yeah, please. This is very recent in a sense. There is a lot of research which is going on in this direction, and it's all inspired by one fundamental paper by David Gale. Okay, he said it is Brouwer's fixed point theorem is essentially game of hex. Okay, yeah, okay, 2 colors would be enough. So, this is purple, this is, oh, I don't want purple, I want blue. Pink. So, you have a girl and boy playing the game. How are they occupying? Okay. Now, blue is occupying. See, the way occupation takes place is, first priority is for the girl. Okay. And the second priority is for the boy. And also, first, each vertex here, the least vertex, if the vertex is least, and whichever coordinate is least, it may be, both coordinates may be least, but if it is the first coordinate is as well as second coordinate, both are least, priority is given to the girl, and that is the color I give. So, for example, this one, minus 0.1, minus 0.1 on the boundary will get what color? Pink. So, this is occupied by the girl. Okay? Now, 0 minus 0.1, that goes to boy. So, all these will be occupied by boy. Okay? Now, you go to the highest value for the x and y coordinate. Again the same preference. If the highest coordinate is the first coordinate, then it is given to the girl. Follow me? If it's the second coordinate, then it is given to the boy. First you fill it up here. Now what will be the color of this? This one has the least, it's going, but the first coordinate is still minus 0.1. Agreed? So the first coordinate is minus 0.1. So this goes to the girl, girl, girl. And this one, this is the highest coordinate. First coordinate is the highest. The second coordinate is the least. For this point, first coordinate is still the least. Is still the least. Therefore, it is still pink. Now come here this way. What will happen? Here, neither the first coordinate of this point is 0. It is not the least. Least is minus 0.1. Least value possible for any coordinate is what you consider. The least value possible for the first coordinate is minus 0.1, but that is not the case here. So this will be, all these things will be blue. Blue. Now what will be this one? Pink. Why? Because both coordinates are highest, but priority is given to the girl. Agreed? Now here, this one will be pink. All these things will be pink, you can check it. Okay? So, my function is not defined at these points. It is not defined at these points. But the function is defined inside the original square. Okay? But there I want to evaluate who occupies. Is it the house of the girl or the house of the boy? You follow me? Is it the house of the girl or the house of the boy? So I need to evaluate the value of the function at 0, 0. Okay? My criterion is the following. You evaluate the value of the function at that point and take the absolute value f1 minus x and f2 minus y. The difference, okay? As long as the very first coordinate is greater than 0.05, it is for the girl. If first coordinate is not so, only the second coordinate is so, then it is for the boy. So now let us look at this one. What will be the color for this? This one. 0, 0. So let's evaluate that. Okay? So f1 of 0, I'm sorry. f1 of 0, 0 is 0 plus 0 plus 1 over 3. Okay? f2 of 0, 0 is 0 plus by 2. So this is 1/3, this is half. So you subtract 1/3 minus the x coordinate, the absolute value, half minus 0, both are greater than 0.05. Both are greater than 0.05, but always give the priority to the first coordinate. Suppose if this difference is less than 0.05 but this one more, then it is the other boy. So this one is going to be a pink. It's occupied by a pink. Do you follow me?
Greater than or equal to?
You can put greater than or equal to, nothing is lost. Nothing is lost.
Condition 0.05.
Oh, 0.05, I see. So that means this is not 10 but it is 20. The division is 20.
condition is depends on the grid size.
Huh?
The condition
The condition depends purely on the grid size. Yeah, you choose the right grid size to work out what level of approximation you need. If you want a further approximation, you divide the grid size into 100, whatever it is. In fact, I had this, see, I have no knowledge of programming. See, I have no knowledge. I have to tell you a story with my student Bapat. We were both sitting in a computer science course. This is a Fortran 101 or some nonsense, whatever it is. So, but what happened was, initially one of the graduate students was teaching the course. And then the problem was, they were telling how to write down the variables, this, that, and all the integer variable. And then one of the first problem was, between 1 and 1000, write a small program to find out which are divisible by 9. And then this was the problem. And then I told Bapat, if this is the case, why waste the time? We could have as well done it. And all he said was, Professor, you already know all the alphabets. All you need to do is only to write Shakespeare out of it. Okay. Now, he asked me to write the program. It was an insult for me that with my mathematical abilities, I should be able to write it down. So I wrote down the program, and he said, your program won't run. Then I ran it. And it printed, 1 is not divisible by 9, 8 is not divisible by 9, 9 is divisible by 9. After that it said 10 is divisible by 9, 11 is divisible, everything was divisible by 9. And then I asked him, where was my mistake? No, that's the problem. That's all the work of computer science. You need to also find where the mistake is. Okay. Then I started respecting computer science. You need to get a beating before you respect that knowledge. Okay. Respect that knowledge. One more example. I was talking about optimal assignment problem. You know what is an optimal assignment problem? No. There are 20 secretaries who are good at typing. And then there are 20 tasks. Okay. Now, each secretary, one task may be to type something about finance, another task may be something about spreadsheet or whatever, some nonsense, different kinds. So each secretary has an ability, takes a certain amount of time to finish typing that. Okay, time taken. So the time taken is given as a matrix. The ith secretary taking the jth job, the time taken is Tij. So our problem is to assign each secretary a task so that the total time taken by all of them is the least. Okay. So this I presented at Madurai University, and there was an algebraist. He said, I don't see any great mathematics in this. Okay. And all you do is take one at a time and then finish it up. Okay. Try every combination, and one of them is going to give the answer. And then I said, suppose if there are 50 secretaries and 50 jobs, and if you tried every combination, and suppose each combination to evaluate takes, say, 1 millisecond, then you can finish this job roughly in 1 billion years. If you try one after the other. So you need to do more intelligent way of finding the solution. So then only he started respecting finite mathematics has a deep insight. And they started, the people who are in pure mathematics, who are always into continuity, will start appreciating only when they are pushed into one such problem. Solve this. And struggling. Okay. But whatever it is. Now, so this one is read. So the procedure is the following. We know if the entire thing gets filled with one of these two colors, if the entire thing gets filled with one of these two colors, it is equivalent to saying either f1x minus x is greater than or equal to 0.05 or f2x is greater than or equal to 0.05. But this is against fixed point theorem. We know a fixed point exists, so it cannot happen. You follow me? If the fixed point theorem is true, then you will not be able to do this coloring for all points. You will not be able to color all the points. Somewhere some point will be there which is an approximate fixed point, where this will be less than 0.05, this will also be less than 0.05. Then who gets it? Is it the girl or the boy? No. If both are less than 0.05, you cannot give it to girl or to the boy. So there should be such a point. We already know that. But the only thing which the algorithm does is, it is not trying to evaluate the value at all these points. That is waste of counting and waste of labor. So an efficient algorithm must search only along some kind of a path. Only along some kind of a path, and at that path somewhere suddenly you are stuck. You are not able to color this way or that way. Then you stop and say that that is the approximate fixed point. So now what I try to do is pretend that everything is colored by one of the two players. Then there should be a winning path by Hex theorem. That's what I mentioned. You remember? That's what I mentioned. And the Hex theorem, there is a winning path. Now in the whatever it is tutorial, I am going to give one such picture, but I want you to go through the algorithm, not by looking at it. By looking at it, very often we can do it, but by the algorithm, because a computer will not know how to look at it. You pretend you are the computer. Okay. Now I am saying the following. First you join this with a triangle. Okay. This triangle has three vertices. One of the vertex will have the same color as another vertex. For example, this and this have the same color. But this is a new one which you evaluated. Previously you didn't evaluate this. So this is an old one which was already evaluated. Whomsoever is the old one, you want to toss it. And use the other two, this and this, to build another triangle with all the three vertices adjacent. When I say adjacent, you remember, two vertices are adjacent if one of them has both coordinates less than or equal to the other coordinates, okay, and the difference is at most 1. So which will be the next point? Is this an adjacent vertex? No, if I have this adjacent, then it will be this triangle. This is fixed. See, the two colors must be there. You toss this one, I am saying this is the next vertex. Are you with me or not? I am saying the next vertex to be evaluated is this. Because if I toss this, and if this is the triangle with one side, what is the one with... So you have, can this be the third one? No, because when I look at this triangle, this one's coordinate 0, minus 0.1. This one's coordinate is 0, 0. Now this one's coordinate is 0, minus, yeah, 0.1 minus 0.1. This is 0, 0, this is 0.1 minus 0.1. They cannot be adjacent because first coordinate is less than the first coordinate, but the second coordinate is more than the second coordinate. So these two are not comparable vectors. So it should not be this. It should be only this. Do you follow me? Okay. So our next evaluation is this. Okay. So what are the coordinates of this point? Huh? Only one of you say. Please raise your hand and I will choose the person. Okay, tell me. 0.1, 0. Okay, now I evaluate the value of the function at this point. Okay, so let us evaluate that. That one is 0.1 plus 1 over 3, xy is 0, 1 over x is 0.1, so 2.1. So 1.1 over 3 and 1 over 2.1, for sure this again the girl gets it. Agreed? So this point is also occupied by the girl. Now, this is the old one, this is the new one. See, the repeat one, whichever repeats, the old one must be tossed and the new one must be taken. So you use this triangle, with this as the side, what is the third vertex? Where all the vertices are adjacent to each other. If this, it has to be only this. Do you agree? So, already it has a color. You don't have to do anything. Now you toss this one, because this is the old one. Okay? Now, what will happen? If I toss this and keep this side, then I will move here. Agreed? So, I need to evaluate the value of this function at this point. This is the procedure. Okay? So, when you do like this one, only you are going along this path of winning path. You are building the winning path this way. And winning path is possible only when the entire board is covered. You will find along this path difficulty in allocating, either to player 1, to girl or to boy. And that is the approximate fixed point. The algorithm is only that, nothing more. But the formal proof of this is quite involved. Okay? But at your level, you should first appreciate the algorithm. Agreed? This is like when we were children. See, you have multiplication as well as division. Okay? My father would ask me some question. What is 7 times 8? 56. What is 14 times 16? 224. Like that, you blurt out fast. Okay. Now, the same question he can ask the following way. Each person is paid 16 rupees. If there are 14 persons, how much I have to give? Then I will ask my father, should I multiply or divide? Okay. That's all the thing which I will ask my father. No, this time I will let you go. Multiply. Oh, 224. This is that kind of a training which we have. It has spoiled, it has helped us to remember many things, but it has spoiled us to think clearly. See, thinking clearly is very essential. That is kind of thing which I noticed in the Western students. From the early days, they are kind of trained to think. In small ideas, even small ideas, they think to write down. They have assignments which are like that. Okay, say 3-year-old child, or second grade, third grade, my granddaughter for example, she is in the 7th or 8th grade. And then she is asked to write something about Kenya and what are the things grown, etc., blah, blah, blah. Okay, so she has to go and dig into the books and write down some nonsense, whatever she knows. Okay, so that way they develop one's own. It's not pumped, you are not pumped with a certain syllabus and vomit it. That's the difference. But I'm sure there is a lot of change which is going on also here. Anyway, that's this algorithm. Now let us look at the algorithm here. Okay? So I evaluated, then it was going to 1 means girl and 2 means boy. Then I traveled like this one, 0.10, 0.20, 0.30, 0.40. Then I came to 2, like that. Can you push the next one? Okay. Now I came to, traveled along this path, I came to 0.7, 0.5. You have to remember, I'm not traveling through all suppose if the grid is say 20 by 20, I'm not searching all the 400 vertices to come to the answer. I'm searching only along a linear path. But the path can be a piano curve also. It can travel hopelessly through everything also. It's possible, but by and large it doesn't do. Okay. So, you take 0.7, 0.5, when you evaluate that, the value of the function is 0.73 and the other one is 0.50. The difference is both are less than 0.05. Both are less than 0.05, so you are not able to assign it either to 1 or 2. And the moment you find it, you have already found the solution. So this is the solution, approximate fixed point solution, and this is used to compute competitive equilibrium price in economics, and a lot of profound work has been going on and it still goes on. And it is extending it to n dimension and is a major work. But one more thing which you have to appreciate, I am only dealing with the square and a cube or n-dimensional cube. What happens if it is some other prism kind of thing? The theorem is also true. So you need to transform the prism problem into cube problem and then work on the cube problem to solve it and transform it again to prism. So this setting up of the what I call the topological homeomorphism between the cube and the prism is in itself an interesting thing, isn't it? You should know what is the one-to-one continuous, inverse continuous map. Okay? So you need to think about such things, and that way there are many open problems there. Sorry. I think I will stop here now. Yeah. Huh? Even if I find the approximate fixed point, the actual fixed point may not even be anywhere close to it. The actual fixed point may not even be anywhere close to it. Unfortunately, that's the situation. All you can say is, this is an approximate fixed point, I am content with that. But if you are grinding at the actual fixed point, no, there is no way. No way. Yes, it's very similar to, for example, quintics cannot be solved by a method of radicals. Okay? And when you see the beauty of the proof, etc., there are many theorems also in stochastic games which we tried to do, and we realized that you cannot do it with your field operations. Order field property doesn't hold and things like that. Yeah. But anyway, with this background, you have an idea of solving for a fixed point and hopefully also finding Nash equilibrium. I will talk about Nash equilibrium as the final thing. Okay.